Hello everyone. In this video, we are going to solve remaining problems of assignment 2. These problems are more related to Grover's search algorithm. Let us look at question number 6. We are asked to find number of iterations required to find a marked state among 64 states. So n is 64. So sin theta is 1 by root 64, where pi by 2 minus theta is angle between marked state and S, that is pi by 2 minus theta is angle between S and W. So for this value of sin theta, we obtain theta as 7.18 degrees. So the angle between S and W, that is pi by 2 minus theta, is equivalent to, in degrees, it is 82.81 degrees. We know that for every iteration, we have a rotation of 2 theta, that is 14.36 degrees. So we need to find out number of iterations in which we can get very much close to this value. For example, we see that after 5 iterations, we will cover around 70 degrees angle, which is close to 82.81. So let us consider 5 iterations. After 5 iterations, angle between S and W would be 82.81 degrees is the initial angle. It is subtracted with 5 times the value 14.36 degrees. That gives us 11.01 degrees. So let us try number of iterations as 6. 6 times 14.36 degrees. That is nothing but subtracting 14.36 from this 11.01, which gives us minus 3.35 degrees. So we can see that in case of 6 iterations, we are very much close to the 0 degrees. So 6 is the answer. In 6 iterations, we were very close to the marked state. Suppose if we take number of iterations as 7, we again need to subtract 14.36 from this value. So we are going far from the marked state. Suppose if we take value as 4, then we need to add 14.36 to this value. Again, we are going away from the marked state. So 6 is the optimum number of iterations. So answer is 6, which is option B. Let us look at question 7. In question 7, we are given 8 different items and we need to find a marked state after 2 applications of Grover rotation. Now we need to find probability of failure. As we have 8 states, amplitude of each state initially would be 1 by square root 8, that is 1 by 2 root 2. A Grover rotation includes application of UW and US. So what does this application of UW does? Application of UW on state S inverts component parallel to W. So our marked state inverts. So after this, we have amplitude of marked state as 1 by 2 root 2 and all other states is 1 by 2 times square root 2. So the mean mean amplitude, as we have 8 different states 1 by 8 times, we have 7 different states with 1 by 2 root 2, and we have a state with minus 1 by 2 root 2. This gives us mean amplitude is referred as A bar. This gives us 6 by 2 root 2 times 1 by 8, which is equal to 3 by. Now, after application of UW, we apply US on the resultant state. Applying US means AX transforms to 2 times A bar minus AX. So, our AW transforms to 2 times A bar, that is 2 times 3 by 8 square root 2, and our AW is, in the previous state, our AW is minus 1 by 2 root 2, which gives us 5 by 4 root 2, and all our AX are transformed to 1 divided by 4 root 2. So, we can see that after one iteration, amplitude of marked state is 5 times the other states. So, the probability of the marked state increases by 25 times with respect to other states. Now, we have completed one rotation. So, in the next rotation, we repeat the same operations. For the next rotation, we repeat the same operations, but with initial amplitudes as 5 by 4 root 2 and 1 by 4 root 2. So, after applying UW again, we have AW as minus 5 by 4 root 2, as this is the marked state, and AX is 1 by 4 root 2, and the new mean is 1 by 8 times, as we have 7 unmarked states which corresponds to 1 by 4 root 2 amplitude, and a marked state with 5 times 1 by 4 root 2 amplitude, and this gives us 1 by 16 root 2. So, the second Grover iteration, we again apply another operation which is US, and applying US means we have already seen that AX transforms to 2A bar minus AX. So, now AW is transforms to 2 times the mean. The previous mean is 1 by 16 root 2. Subtract from, which is 11 divided by 8 root 2. So, the amplitude of the marked state is 11 by 8 root 2. So, the probability of success after 2 iterations would be the square of this amplitude. So, probability of success after 2 iterations is the square of amplitude, that is 121 divided by 128. So, probability of failure is 1 minus 121 divided by 128, which is 7 divided by 128. So, the correct option is option B. Let us look at question 8. In question 8, we are given that n is equal to 8. So, we have 8 items, out of which 1 is marked. It is also given that after I iterations, we have amplitude of marked state as square root of 6 by 7, and the amplitude of other states is 1 by 7. So, we have that Ki, which is amplitude of marked state, as 6 by 7, which we can consider as AW, and all other AX is 1 by 7. What we need to find is Ki plus 2, that is amplitude of marked state after 2 iterations. We perform similar operations as previous. We need to perform 2 iterations, that is we need to perform UW, US, again UW, US in order one after the other. Performing similar operations as in the previous problem, we obtain mean in the first iteration as 1 by 8 times 1 minus square root of 6 by 7. So after applying US, we obtain AW as 2 times mean subtracted from negative of this. So directly that means we are adding root 6 by 7 to the 2 times of mean, which gives us on all other states we have 2 times mean subtracted with 1 by 7, which gives us so again we find mean for the next iteration, which is 1 by 8 times 7 times AX will give us 3 by 4 minus 7 by 4 root 6 by 7, and we calculate mean after applying UW. So applying UW makes AW2 minus AW, which makes it minus 1 by 4 minus 3 by 4 root 6 by 7. So mean in second iteration is 1 by 8 times half minus 5 by 2 times root 6 by 7. So after operating US, AW transforms to 2 times mean added to the previous AW. So 2 times mean is 1 minus 5 root 6 by 7 added to the previous AW, which is 1 by 4 plus 3 by 4 root 6 by 7. This gives us 1 by 8 times 1 minus 5 root 6 by 7 plus 2. Multiply and divide with 2, then we will obtain 2 by 8. Take 1 by 8 as common, so we write plus 2 inside the brackets plus 6 times root 6 by 7. So the amplitude of marker state after 2 Grover iterations is 1 by 8 times 2 plus 1 3, 6 minus 5 1 plus root 6 by 7. So the correct option is A. Let us look at question 9. In question 9, we are asked to find the probability of success of Grover's algorithm after optimal number of iterations for large n. So we are assuming that n is very large here. N very large. Sin theta, where theta corresponds to theta is such that pi by 2 minus theta is angle between S and W. Here we have sin theta is equal to 1 by square root n. As n is very large, 1 by square root n would be very small. When sin theta is very small, we can approximate it to theta. So theta is 1 by square root n. Say m is optimal number of iterations. So after optimal number of iterations, the angle covered by the state would be m times 2 theta, which should be ideally matched to pi by 2 minus theta, which is initial angle. M times 2 theta is angle rotated and pi by 2 minus theta is angle initial. So, if you are able to cover the initial angle after m iterations, then we have successfully obtained the marked state. So, substituting theta as 1 by root n, we obtain m is equal to pi by 4 times root n. But amplitude of the marked state after m iterations would be sine 2m plus 1 theta. This is because after m iterations, angle between the two states would be pi by 2 minus 2m plus 1 theta. So, the amplitude should be sine of this angle. As the angle between S and W after m iterations is pi by 2 minus 2m plus 1 theta, we have amplitude as sine of 2m plus 1 times theta, which is sine of pi by 2 root n plus 1 times 1 by root n, which is again sine pi by 2 plus 1 by square root n. This is cos 1 by square root n. When considered n is very large and m as optimal number of iterations, we obtain amplitude of the marked state after optimal number of iterations is cos 1 by root n, which can be approximated as 1 minus 1 by 2n when higher order terms are neglected, and we need the probability of success, which is square of amplitude 1 minus 2 times 1 into 1 by 2n, that would be 1 by n plus 1 by 2n whole square. As n is very large, we can neglect the term 1 by n square and we obtain 1 minus 1 by n as probability of success of Grover's algorithm, which is option B. Now let us look at multiple select questions, where first two questions are corresponds to constant functions and balanced functions. We need to know which function is a balanced function and which function is a constant function. So let us consider option wise. A is given as f of x equal to sin x, sin pi x. So change the values of x. Say, let us construct a table. Change x as 0, 1, 2, 3, 4. And this option A, B, C, D. Option A is sin pi x. Sin pi 0 is 0. Sin pi is 0. Sin 2 pi is 0. Sin of integral times pi is always 0. So this is a constant function. Option B is f of x is equal to sin pi x by 2. Sin pi by 2 times 0 is 0. Sin pi by 2 times 1 is 1. When we substitute x equal to 2, we obtain sin pi, which is 0. Similarly, we obtain When x is equal to 3, it is sine 3 pi by 2, which is minus 1, 0. So this is not a constant function. Option C, f of x is cos pi x. When x is 0, cos pi times 0 is 0, cos 0 is 1. When x is 1, cos pi is minus 1. When x is 2, cos 2 pi is again 1. So this is also a not constant function. Option D is f of x is equal to mod cos pi x. It is just modulus of the previous function. So we have all 1, 1, 1. So this is a constant function. In the question we are asked to find which of the following are constant functions. We see that option A and option D are the correct options for constant function. Let us look at question 2, where we are asked to find which of the following is the balanced function. Let us construct a table similarly. Option A, B, C, D, and X 0, 1, 2, 3, 4. Option A is sin pi x. In the previous question, we have seen that sin pi x is a constant function. Because sine of integral times pi is always 0. Option B is sin pi x by 2. As we change x, when x is 0, the value is 0. When x is 1, it is sin pi by 2. When x is 2, it is sin pi 0. But when x is 3, it is sin 3 pi by 2, which is minus 1. We see that it is not a balanced function. Option C is option C is modulus of sin pi x by 2. So simply apply mod to the previous function 0, 1, 0, 1. As we go on, we obtain 0, 1 alternatively. So this is a balanced function. Option D, f of x is equal to mod cos of pi x by 2. So when 0 is substituted here, we obtain 1. When 1 is substituted, we obtain 0. And when 2 is substituted, we obtain cos pi, which is minus 1, and modulus of it is 1. When 3 is applied, cos 3 pi by 2 is 0. So we have obtained 1, 0, 1, 0 alternatively. Similarly, if we calculate all, we will obtain 1, 0 alternatively. Or even we can prove it generally, taking x as odd and even. So this is also a balanced function. So when we are considering balanced functions, the correct options are C and D. Yeah. Let us look at question number 3, which is based on Simon's algorithm. Here we are given a table x corresponding f of x, and we are also given corresponding xi, which is 1, 1, 0, and we're all, as we know that Simon's algorithm is initialized with state, initialized with state 1 by 8 times sigma with 0 0 0 in the second register and all the possible states of 3 qubits in the first register. So when we apply the oracle, we know that the second register contains f of x values corresponding to the x. And now in the question we are given that observation on second register has given the value 110. Output of second register. This measurement on second register gives us 110. So the state which is obtained after applying the oracle is now collapsed such that the second register is contained 110 qubit. So the first register would contain qubits such that their second the first register may contain values which are in synchronized with the second register. So we need to find x which has f of x as 110. Obviously there will be two different values of x which have f of x as 110. By stating that measurement on second register gives 110, we are told that what are the possible states of x? What are the possible states of x? So the possible values of x are 0, 1, 1 and 1, 0, 1. So first register contains a linear combination of 0, 1, 1 state and 1, 0, 1 state. So now applying Hadamard gate on this state would give us applying Hadamard on 0 gives us applying Hadamard gate on 1 gives us similarly for the next term. The output is, let us calculate this explicitly, 1 by 4 times multiplying these two would give us 0, 0 minus 0, 1 plus 1, 0 minus 1, 1 times 0 minus 1. This second term corresponds to the term qubit 0 minus qubit 1 times qubit 0 plus qubit 1 times qubit 0 minus qubit 1, which are the outputs of Hadamard gate with these respective inputs. So the second state after calculation is So we see that the second term in these expressions is same. And now looking at the first term, we see that 0, 0 has the same sign, and qubit 0, 1 and 0, 1 in the second term are different. So when we expand these terms would get cancelled out. So the output would be 1 by 4 times 2 times the terms whichever remains are doubled because there are two terms of similar kind. So the final output we obtain is 1 by 2 times qubit 000 minus qubit 001 minus state 110 plus state 111. Now looking at the options, option A is correct because the state 00 is present, and option B is also correct because state 001 is present. Option C, which is 011, state doesn't exist among these, so C is wrong. And option D, which is state 111, is also included in the linear combination of the output. So option A, B, D are correct. Now let us look at question 4. In the question 4, we have a database of 16 items, and one of them is a marked state. We are asked to find the probability of the failure after n iterations of the Grover's algorithm. In the options, we are given combinations of number of iterations and corresponding failure probability. We have n is equal to 16. So the amplitudes initially would be 1 by 4. So amplitude of marked state is 1 by 4, and also all other states has amplitude 1 by 4. So after applying UW, AW is minus 1 by 4 and AX is 1 by 4. So the mean is 1 by 16 times 15 times 1 by 4, and we have minus 1 by 4, which gives 7 divided by 32. So when you apply US gate, we obtain AW as 2 times the mean subtracted with AW, which is minus 1 by 4, which results in 11 divided by 16, and AX is 2 times 7 by 32 minus 1 by 4, which results in 3 by 16. So after having one iteration, the probability of success is square of 11 by 16, and probability of failure is 1 minus probability of success, that is 1 minus 121 divided by 256, which is 135 divided by 256. So the option D is one of the correct choices. Now going to second iteration. At the end of first iteration, we have AW as 11 by 16 and AX as 3 by 16. So after applying UW, we have AW as minus 11 by 16 and AX as 3 divided by 16. So the mean would be 1 divided by 16 times, here we have 15 unmarked states. So the mean is 17 divided by 8 times 16. So when US gate is applied, we obtain AW as 2 times mean minus, which is 17 divided by 64 plus 44 divided by 64, which is nothing but 61 divided by 64. So the probability of failure is 1 minus 61 divided by 64 square. Calculating this, we obtain the answer as 375 divided by 4096. So for n equal to 2, we obtain p equal to 375 divided by 4096. So option B is also correct. As we have already seen, D is the correct answer, and now see B is also correct answer. Effectively, we can conclude that A and C are incorrect choices. So B and D are correct choices for this question. In this assignment, we have solved many problems based on different quantum algorithms. We have extensively dealt with Grover's search algorithm. In the coming lectures, we will deal with Shor's algorithm. In the next assignment, we will deal with more problems on Shor's quantum algorithm, which is based on factoring a given number. So here we end this assignment.